So as we already know how the secant method operates, and what is, you can say, the general form of the secant method, how we can use the secant method in our you can say how we can use secant method to calculate the root value of any function, as we did in the example. So now what we need to do is we need to write the function, our own custom function in the Matlab for the secant method, so that we can, whenever we call the secant method, our custom function, and give it some function, just like in the example x cos x plus 1. So it may calculate, or it may use that function to give us the value of the root. So just as we did with the you can say Newton method, Newton method in the Matlab, we will, you can say, follow the similar lines here. So we will start our function, we can write function, and we need to, you can say, give the, you can say, the outputs of the equation. So similar to the what we did with the Newton method, we can get the, you can say, two values. First one, we can say the r, and second one is n. So we are getting, you can say, the root value and the number of iterations it has run. Alright, so it is very similar to what we did in the Newton method. So we can name our function to be secant, and we have to define the number of inputs. So you know that what are the inputs here. So basically we need the function value, and we have to give how many points? We have to give 2 points. So instead of 1 point in the Newton method, we have to give 2 points, x1 and x2. And what other thing we can give it? Maybe the tolerance and the maximum number of iterations, we can say it n. So as we have defined, you can say what will be the inputs and what will be the outputs of the function. So we can come to write down the function. So we can first use the similar command we use in the Newton method, which is like we can define the function f to be Matlab function. So you know that why we do this, so that whenever we use f, our Matlab can refer to the function f. Alright, so we are defining f to be a Matlab function inside this, you can say, code. So whenever we use f of 3 or f of 2 or f of any value, so it will put that value in the function. Alright, so next we could define, and you can say, the x vector, which could include initially the zeros, like we did in the Newton method, and we want it to be one row and how many columns? N plus 1. So you know that with each iteration it is increasing one value. So it is working on the similar lines as did the Newton method. So now we need to calculate. So we can write our for loop, and we can say, similar to the Newton method, that n can go from n is equal to, you can start with 2 to n. Alright, in the Newton method we started from one value. Alright, so here we are doing it from, and one major thing you have noticed that, and we have in the Newton method we did some initial check that f prime of x should not be equal to 0, whereas this is not any condition here. So what could be the failure here is that someone may input the values of x1 and x2 to be the similar values. Alright, so if x1 and x2 lie on the same point, or are given, for example, if someone gives the value of x1 to be 1 and similarly x2 to be 1, then our you can say the secant line could not be drawn. Alright, so this is a problem. So we need to make sure that this not happens. Alright, so we can do it similar in the similar manner by writing you can say an if statement. If we can say that if x of 1 is equal to x2, then the root value is basically root is equal to, we can write failure. Alright, and you know that if this happens, we need to give r is equal to failure, and we need to end, or we need to come out of this function. So we use the return command. So all of these code are basically, I am, you can say, accumulating the knowledge of the previous lectures and videos. Alright, so we started with the bisection method, and then we move on to the regular falsy, then we discuss the Newton method, and then we are coming here to the secant method. So you must refer to these videos, the earlier videos, if something here is not very you can say, understandable for you. So now we are now, you know that we have defined this this, you can say, a vector with the zeros with one row and n+1 columns. So you know that the initial value of this, you can say, the vector is x1 and x2, which are known to us. So you must set these two values in our vector. So how we can do that is we can define that x of 1 should be equal to what is our input, which is x1. Alright, so we have defined that, and now what we need to do is we have to define that x of 2, the second value of the vector x we have defined here, should be equal to x2. Alright, so you can use this semicolon to, you can say, shun the command. So after doing that, what we need to calculate is xn+1 based on that formula. So we can calculate xn+1. So you can see that why we have used n is equal to 2 is so that when we write the formula of xn+1, so you can see the n is equal to 2. N is starting from the 2 value and it is moving onward. So we can use n is equal to 2. So when we put n is equal to 2 here, it will give x3, which is what we required and what we can start from. So we can write, you can say, our this formula. We can write x of n+1 will be equal to, so x n+1 is equal to x of n minus, you can use two, you can say, brackets, x of n minus x of n minus 1, and close the second bracket, and divided by f of x of n minus f of x of n minus 1, and we need to close this bracket and the one again, and then we need to multiply it by f of x of n. But I hope that I have written this formula correct. Let me check it again. So you should also, you can see from here, so it is already based on the similar lines. Let me check it again. So I think it is quite correct. So now that we have find out, we have written the formula. So when the n will be 2, this will calculate, or this will calculate x3 value and save it to the entry number 3. And you can say on the third place, on the third column of the vector x. So vector x basically is keeping record of all the x values we are calculating or the x values we have. So after calculating, what we need to do is, as we did in the Newton method, we need to make sure that it is, you can say, if the tolerance level of our, you can say, uh, tolerance level we have given to the function is already achieved, then we must finish our function, or we must finish calculating the task. So we can use the similar code, which is that we can find that absolute value of x n plus 1 n plus 1 minus, minus uh, x of n is less than the tolerance value which we have input, then r is equal to x of n plus 1 and return. Then we need to use the AND command to close this if loop, and we can also close our AND loop. So this is basically you can say what we did here in the line of code from 17 to 20 is that we are saying that if if x2 minus x1, or if whatever you can say n plus 1, the next root value or the next x value is minus the next in the previous value is, you can say, less than the tolerance value. Sorry, so less than the tolerance value. So we must end the, you can say, we must end the code, and the x n plus 1 value, the x value which is, you can say, the most recent one, is basically x n plus 1 is basically what it is our required root. So you should we are asking the, you can say, the computer to give the value to be x n plus 1 and just finish everything by using the return command, and we are ending the statement. Alright, so this is you can say what we can do here. So what we need to do next is save this file, save this m file in the name secant.m, because the Matlab is auto-detecting that it is a function, so it is giving us the name of the function at the place. So you can just save it out. So now that we have saved the secant, you can say the secant function, what we need to do is we need to call that function and solve our problem, what we did in the example in the lecture, in the previous lecture. So we can use the similar method we did in the Newton method. So we can use the sims command, syms, to define that our variable is x, and we can write our function f is equal to, what is it, we have to use these brackets, and we can write our function then x multiplied by cos of x and plus 1. So we have defined our function, and what we need to do is you also know that similar to the Newton method, our function secant also give us two values. So you can use two variables to store the value of the root and the number of iterations. So let's say we use r, you can use r or n also, or you can use maybe root or n, or you can say times, or so we can say times, or we can use iterations. So it doesn't matter. All right, so it will give two values, and we can store these two values in any two, you can say, variables we define. It could be a letter, it could be a word, whatever we want. All right, so now we need to call our function with the name with which we have saved that you can say function. So it is secant, and what we need to do is we need to give the inputs to the function. And you know that the first thing we need to give our function was the f value, the function which we have defined here. All right. So the next thing we need to give is x1 and x2. So similar to that we did in the example, we can give it the value x1 to be 1 and x2 to be 1.5. All right. So what other thing we need to give it was the tolerance value. So we can define it to be 1 e raised to power maybe let's say -4. All right. So and we need to give the maximum number of iterations we want, and we could define it to be maybe 20. All right. So we can run. It will ask us to save. Let us save it to maybe Untitled 6. And when I run this command, oh, Cox, this cause basically. So let's just run again. Alright, so you can see that the root value is 2.073 and iterations are 6. So I think the same, you can say, same number of, you can say the tolerance would be achieved a little bit easier in the Newton method, because we have studied that the Newton method has more, you can say, the convergence ratio than the secant method.